Assalamu alaikum. Hello everybody. Today in Math Club at Kuwait University we will have a lecture about graph theory. The title of the lecture is The Wonderful Land of Graph Theory. The lecture will be presented by Dr. Mohammad Ghebleh. Dr. Mohammad Ghebleh is one of the members in research group in graph theory and combinatorics in math department at Kuwait University with Dr. Ali Kanzo, Dr. Abdul Azmi and others. This lecture aimed to introduce a relatively modern branch of mathematics, graph theory, and it has a lot of applications in different areas such as networks, computer science, sociology, and others. Hopefully, Dr. Mohammad will present some of the applications. And this lecture also aimed to motivate the students, and especially undergrad students, to take a course called Graph Theory number 326 as an elective course in undergraduate math program in Kuwait University. And I will let you now to Dr. Mohammad Ghebleh to present his lecture. And
thank you.
Yeah, thank you.
Okay, good afternoon, everyone. So as you can see from the title, it's a pretty general title. I was struggling a little bit in terms of selecting what to present today. And then I decided to basically show you the path that I took when I started more or less with graph theory. And I will stop, if we have time to cover everything, I will basically stop where I started doing research. So you will see a lot of the motivation, and I started my undergraduate studies in 1993, and 97 I started my master's, and therefore the research that I did is affected by what was hot in the 90s, and it's still hot, but I mean back then there were a lot of activity, a lot of papers, and so on. So I will start with some basic graph theory to show you the sort of nature of things and some small proofs. And then I will advance to more advanced topics. I don't think I will get into many applications. My focus will be on pure side of the graph theory. But applications, I mean, what is a graph? A graph basically is a mathematical model for a situation where you have some objects and you have relations between pairs of them. So, like for example, the nice example that these days everybody mentions is Facebook. So you have many people on Facebook. Some of them are friends with each other, some of them are not friends with each other. And that creates a network for you, right? A network of people on the platform, which is Facebook. And in the abstract, I mentioned sociology, basically. When you have a society of people with the connections between them, you can basically study the properties. For example, like if you find one person who has done something wrong, let's say they are a terrorist, then there is a good chance that in their network or in their second network, like friends of their friends, you will find some people who are basically involved in a similar thing. So you can sort of narrow down your search. But anyway, for me, I prefer to focus on the pure side because I studied the pure side, and I think it's beautiful enough for you to appreciate the subject. But if you're interested in the applications, we can also talk about those later. So anyway, this is where I stole the title from. This is a book called The Fascinating World of Graph Theory. It's a nice book. It is focused on presenting graph theory sort of like the same way that we want to do today, sort of selling it. While most books, textbooks, they start by assuming that, okay, you are interested in graph theory, that's why you have purchased this book or registered in this course, and they start teaching you the topic. But this one is also I mean, it also includes some motivational parts. But anyway, just give them credit for the title. I mentioned historical roots of graph theory. One of the historical roots is in the work of Cayley, who was a chemist. And he was interested in different isomers of chemical compounds. And basically, if you look at organic chemistry, you have carbon and hydrogen atoms. And a molecule involves bonds between the different atoms. So you can represent each atom by a dot and connect them by a line if there is a connection, if there is a bond between them. And you can remove the hydrogen atoms because they have valence 1, so they basically, I mean, if you have just the carbons, it's clear where the hydrogen atoms are. So this is what I will define later as a tree, and basically Cayley was interested in counting how many different trees can you make using, let's say, 4 carbon atoms, and that would be the number of isomers. This is another example of an electrical network, which can be translated to a graph, and the work of Kirchhoff with his 2 laws of electricity actually was to understand the current in the network, and that involves finding what we will call spanning trees, again trees, in the graph. And we are not going to get into details of that. Personally, I don't know much about that myself. So the mathematical side starts with a puzzle. And this is the cover of another book called Graph Theory 1736 to 1936, so 200 years. 1736 is the year where the first paper in graph theory is published by Euler. And it involves the solution of what is called the puzzle of bridges of Knigsberg. Now, Knigsberg is a city in Russia, and there is a river. And in the river, you see an island here, and there is a bigger island here. And there are some bridges. Now, in this picture, it's not that clear, but I have a better picture to show you. There are 2 bridges here, 1 here, 2 here, 1 here. And the puzzle was that people wanted to see if you can start from any area in the city and cross each bridge exactly once, not more than once, not less than once, and go back to the place that you started, or even not, I mean, even if you don't go back to this place that you started, you want to cross all the bridges. Now, this was a puzzle that people were interested in. They would even go and walk on the bridges, trying to solve the puzzle. Now, Euler came along, and this is actually from his paper. He drew this, and the idea for solving this is very easy. Now, you can imagine, if the answer was yes, it is possible, then somebody would find a way, right? I mean, by just walking, or someone would be smart enough or intuitive enough to find a way. So the answer is no, you cannot do that. And the idea of solution is simple. What Euler said, he said, if you take a bridge, let's say you take this bridge to enter A, then you will be taking a bridge to exit A. And since you don't want to repeat any bridges, that means you take a different bridge, right? So every time you enter A, you're also exiting A. That means you're using 2 bridges. Now we have 5 bridges, right? So that means you take 2 and 2, and then 1 is left. So the argument is very simple, is that you want the number of bridges to be even, otherwise you cannot do it. Now, if you say, okay, we are allowed to start in some place and end in another place, then your origin can have an odd number of bridges, and your destination or your final place that you stay will be allowed to have an odd number of bridges. But the middle of the way, all the places that you visit, you must have an even number of bridges. Now, that does not happen here because we have 4 regions. You can see A has 5 bridges, D has 3 bridges, C here has 3 bridges, and B also has 3 bridges. So 3, 3, 3, and 5, all of them are odd numbers, and therefore you cannot satisfy the conditions of the puzzle. Okay? Now, what happens here is that it's not really important what is the shape of A or the fact that A is the geographical position of A is in the middle between B and C or to the left of D. These are not really important. What is important is that we have a region A and B and C and D, and we have 2 bridges between A and B, 2 bridges between A and C, 1 bridge between A and D, and so on. So this is what really matters. So you can see the graph appearing here. We have the regions, which will be our objects, and the relation between them will be if there is a bridge, right? Actually, in this case, we don't get a graph. We get a multigraph because there are 2 bridges between A and B, but it's okay. That would be a generalization of the definition of a graph. So let's go to the definition, the mathematical definition of a graph. Ignore the picture for now. A graph is a pair of objects, 2 sets, V and E. Now, V is a set like this one, U, V, W, X, Y, Z, objects. So in our example of Euler, that would be A, B, C, D. And E is a collection of subsets of size 2 of our set V. So basically, U and V means that U and V are related, like there is a bridge between them, or they are friends on Facebook. But if you don't see W and Y here, that means there is no relation between them. Now, the drawing is a nice way of representing this because you can put points for the vertices, as we call them. This is the plural of vertex. And they used to be called nodes. Still, some books might call them nodes. That's fine. And edges are represented by line segments or, in general, by curves joining 2 points. Now, you can start talking about the topology of such a drawing, but actually the drawing itself is not significant in graph theory unless if we want to talk about it, and we will get to that later. Like for example, here you see there is a crossing between ZW and VY. This does not really matter. I can take this node Z and slowly move it in the middle of the foregone here, and then you will see there will be no more crossings. I can take U and draw it here, and then there will be more crossings. It's not important. What is important is that there is an edge between a pair of nodes or vertices, or there is no edge between. So any binary relationship can be modeled by this object, right? By this object that we call graph. But usually people, when you talk about graphs, people will be thinking about a picture like this one, including myself, because pictures are easier to visualize as opposed to formulas. I mean, if I give you this set of edges, of course everybody understands that, but how can you really relate to that and think about that? That would be very difficult to do, at least for me. Okay. So at any time during the talk, if you want to ask questions, please do. I mean, don't wait for the end. So I'm going to mention some quick terminology. The number of vertices is called order of a graph. So this one has 6 vertices. It has order 6. The size of the graph is the number of edges. The degree of a vertex, so like, for example, this vertex V is the number of edges that initiate or end at this vertex. Now, in this case, we don't have directions on the edges, so it doesn't really matter. It's the same thing. So I have 1, 2, 3, 4 edges at V. I have UV, VW, VY, and VZ. So the degree of V is 4. Now, in terms of our previous example of the bridges, we want the degree of each vertex to be even. This is on the slides later. A path is walking from one vertex to another vertex along the edges. So if I want to go from V to X, I can go V to Z, Z to W, W to X, or I can go V to W to X. These are called path in a graph. A path usually is not allowed to repeat vertices. So I could go, let's say, from V to U to V to Y to X, but then I would be repeating the vertex V. And for a path, this is not allowed. But we have different names for the other types of walking on the graph. Actually, what I just described is what we call a walk, not a path. This graph is a connected graph. How do we decide if a graph is connected, or how do we define it? Between any pair of vertices, we want a path. So we want to be able to walk from each vertex to each other vertex. So the definition of connectedness would be based on the definition of path. And the theorem of Euler says a connected graph is Eulerian if and only if all vertex degrees are even. Now, Eulerian, I did not define it, but you can guess what it means. It means you are able to start at a vertex and walk along the edges to other vertices in a way that you use each edge exactly once. So you don't want to repeat any edges, and you don't want to miss any edges. So edges are our bridges. We saw that if this is possible, then all the vertex degrees must be even. This is very easy because as you enter a vertex, you must be able to also exit. So you will be using the edges in pairs. But the opposite is also not that difficult to show. This is usually in a graph theory course. This is done in first or second week. You can very easily construct a path. And generally, what happens is that you start walking on the graph. Because all the vertex degrees are even, as you enter a vertex, you have a way of exiting because you have used only one. And you keep walking until you get stuck and you have no more options. So if you get stuck, that means you're back into the original vertex that you started from, because all the vertex degrees are even. And now it is possible that you have missed some edges along the way, but you can actually revisit your walk, and at that vertex, because there are some unused edges, you take a detour. So the proof, if you want to write it with details, will be a little technical, but it's not that difficult. And I hope that you get the proof, at least the idea of the proof here. To continue with our terminology, this is a cycle in this graph. A cycle is starting from a vertex, going back to the same vertex without repeating any vertices again, like a path. And this is another cycle, so the edge crossing that we saw earlier is not really a problem. This is V, W, Z, Y, V. So, I mean, when you talk about a cycle, you don't really talk about the drawing of the cycle. You talk about the set of edges. A graph that does not have any cycle is called a tree. Now, remember, Cayley and Kirchhoff, both of them were interested in trees, right? So a tree is a graph that does not have a cycle. Now, the name tree comes from the fact that you can draw this in a way that, like, you have a stem and there are branching, so that's why this is called a tree. And we have a very basic, simple theorem, which says the number of edges in a tree is always one less than the number of vertices. And this is very fundamental, very useful, and at the same time very easy to prove. And the proof is this way. So when you have a tree, you always have a vertex of degree 1. Why? Because if you don't have a vertex of degree 1, every vertex will have degree at least 2. So you can start from a vertex and start walking. And as you walk, any vertex that you enter, because the degree is at least 2, you can exit. And eventually you will get stuck because we have a finite number of vertices. So when you get stuck, you have a closed walk and you can trim it if needed, and you will get a cycle out of it. So you have a vertex of degree 1, let's say this one. Now if I delete this one from the tree, also it deletes one edge, right? So by deleting one vertex and one edge, I get a smaller tree. And this is the induction step for us. I can start from a tree with only one vertex, which has 0 edges. And then, of course, the number of edges is 1 less than the number of vertices. If I have a bigger tree, delete a vertex of degree 1, and you get a smaller tree with n minus 1 vertices, which will have n minus 2 edges. Now put the vertex and its edge back, you will get n vertices and n minus 1 edges. So this is another one of the basic proofs that I mentioned I want to show you because they sort of show the nature of what we do in graph theory. And I have a spanning tree highlighted here. I will not be using this later in the talk, but because it's related to Kirchhoff, and I already mentioned that. So a spanning tree is a tree in a graph using the edges of the graph. So it's a subgraph of the original graph. But you want to use all the edges. That's why it's called spanning. It spans the whole graph. Okay. Another elementary result which is interesting. If you have a graph and you sum all the vertex degrees, it will be an even number. Now this is sometimes called the handshaking lemma. The story is that at a party, some people shake hands with some other people. And if you count how many people have shaken hands an odd number of times, the total will be even. So that's another little puzzle that is sort of classical. But actually, the even number is 2 times the number of edges, which is interesting. How do we prove this? Is a simple, what we call double counting argument. Now, double counting arguments in combinatorics are very common. So you want to count how many elements are in a set. So you count them in one way, you get an answer. You count them in another way, you get another answer. But since you are counting the same objects, that means you will get the same answer. So let's say in this room, this is actually exactly what I am about to do. I can count in each column how many of you are sitting, and then total them. Or I can count in each row how many of you are sitting, and then total. And of course, I will get the same answer, right? So for our graph that we had earlier, I can make a matrix, which is called the incidence matrix. So for each vertex, I dedicate a row of the matrix. And for each edge, a column of the matrix. Now, at the entry ij, I put a 1 if, let's say, u is a vertex of E1. And I put a 0 if it's not, right? So for example, E3 is here, which is V to Z, right? So if you look at it, it has a 1 in front of V. It has a 1, now this is Z and this is Y. I forgot to fix it. And everything else is 0. Okay? I was using different letters, then I changed the letters and I forgot to fix it. But you can see. This is X, this is Y, this is Z. So if I add one row, let's say for W, how many 1s do I see here? At W, I will have a 1 in front of, or under E2, 1 under E5, 1 under E6. So I will get 3, which is actually the degree of W. And same holds for all the vertices. So when I add them, I will get degree of u, degree of v, degree of w. And if I total all of these, which would be the left-hand side of this equation here, I will get the number of ones that I have in this matrix, or the total summation of all the entries. Now, if I look at one column, for an edge E, I have 2 ones exactly, because it has 2 ends. So the total will be 2. And of course, for all the columns, I will get 2s. And when you add all of them up, you will get 2 times the number of edges, which is what we have on the right side. So the total number of ones in the matrix would be the total of the degrees, and at the same time, the 2 times the number of edges. So these two are equal. So this double counting is very common, and it has, you can prove very surprising facts using this one. And I have tried, I don't know if you agree or not, but I tried to give you some of the sort of beautiful, simple proofs, not technical ones. Of course, like any other branch of mathematics, we have very technical, dirty proofs as well. But we want today to have a sort of a nice, easy presentation, hopefully. So do you have any questions up to here? Because I want to transition to another topic now. Okay, this finishes the first part, which is sort of the elementary, basic definitions part of the talk. Now, one of the famous problems in graph theory, which is actually the driving force behind maybe, I don't know, I don't want to give you a number, but a lot of the graph theory that we know today is motivated by this problem. And this is called the four-color problem. Now it's the four-color theorem. But what it says is that if you have any map, now here we have a tiling of rocks on the floor, but if you have any map of countries and you want to color the map, as is usual, you want for neighboring countries to have different colors so you can distinguish them, right? So how many colors do you need, in terms of the minimum number of colors? Of course, in the old days, if you wanted to make a color print, if it was 2-color or 4-color or 8 colors, the cost would be different. So you want to really minimize the number of colors. And the answer is that 4 colors are always enough, which is a little surprising, as I will explain why. But this is the problem. Can every map, every plane map, and we need to define what we mean by a map, be colored using 4 colors so that neighboring regions get different colors? Now, why did I say it is surprising? Because if you look at this simple map with only 4 countries, so A, B, C, D, you can see that A and B share a border, so they must receive different colors. A and D, B and D, they must receive different colors. And C is a neighbor of all 3 of them, so that one also needs a new color. So we need 4 colors for this map. And 4 is enough, of course, because we have only 4 countries. So if such a simple configuration needs 4 colors, you can imagine, okay, I can make a more complicated configuration, and I will need definitely more than 4 colors. But actually, the surprising fact is that no, this is not possible. Any configuration you can make will need at most 4 colors. Okay? Now, this was, I think, open for 300 years. People were working on it, mathematicians, non-mathematicians, many enthusiasts. Actually, the problem originated by a person who was just a mathematics enthusiast, because this was not part of classical mathematics when it started. So understandably, mathematicians were teaching their calculus and their topology and whatever. Actually, enthusiasts were working on this. And there are examples of mathematicians who said, yeah, this problem is not solved because no smart person has really worked on it. And then they worked on it for a month and they couldn't solve it. So anyway, this was open until 300 years. And even now, there are people who are not satisfied by the proof of it. So it is, I mean, if you're sort of interested in conspiracy theories, there are still people who do not believe this theorem. But it is proved, settled in 1976. A lot of graph theory as we know it today actually originates from wrong proofs of the four-color theorem. So a person thinks that I have proved the theorem, this is the proof, he publishes it, and after 10 years or after 2 years, somebody finds a flaw in the proof and they show that the proof is wrong. The proof is wrong, but the techniques actually stay in graph theory and they prove other things for us. So this has been a very fruitful problem. The way that we solved it in 1976 was that they reduced the problem into simple cases, and I touch on these later. And when they reduced it to a simple enough case which could be solved by a computer program, they actually wrote a computer program which would check thousands of cases and see that all of those cases can be colored by 4 colors. So that means the original problem is true. The reduction is not very complicated, but if you make more complicated reductions, then you will have to check fewer cases. And actually, the original proof had flaws in it, but these were flaws that could be fixed in terms of missing configurations and these kind of things. So now what I want to do with this is that I want to actually make it in terms of graph theory. What does this mean for graph theory? Naturally, you can see that the objects we are talking about are the regions or the countries, right? And the relation between them is if they share a border or not. So I can make a graph out of this. Like I have region A, B, C, and D. And if they share a border, I draw an edge between them. In this case, of course, I will have all the possible edges, which gives me what we call the complete graph. Complete graph is a graph which has all the possible edges in it. So in this sense, I don't need to draw a map anymore. I can just focus on the vertices of a graph. So for example, this configuration that you have here, I could probably draw it in a different way. I don't know, I could draw a rectangle and a rectangle in the middle and I don't know, something like this. Now you can see that it's basically the same shape. Instead of circles, I have drawn rectangles, but geometrically these are different, right? So for solving the problem, we don't need to worry about the geometry. We worry about only the graph structure that is underlying that geometry. So this is the general problem. A graph coloring or a proper coloring of a graph is when you want to color the vertices of the graph. Remember, for each region we put a vertex, right? So you color the vertices in a way that adjacent vertices, that means vertices which are connected by an edge, receive different colors. So here I have green here, and red here. Of course, these two reds are not connected with each other by a direct edge, so there is no problem. But this one and this one, since they are connected, they cannot have the same color. Now, of course, you can do this just if you have n vertices, use n colors, right? So all the vertices will get different colors. But the question, which is also inspired by the four-color theorem, is what is the minimum number of colors that we can do this with? Now, in this particular graph, you can see that I need at least 3 colors because I have a triangle here, this vertex, and this vertex. They must get different colors. So I need at least 3 colors. And I think I'm using only 3 colors here. So 3 is the minimum number. I already mentioned this. So the notation is chi, the Greek letter chi of G is the chromatic number of G, the smallest number of colors which can color the vertices of the graph. You can understand that usually we would use numbers for colors. It's easier than having like a set of crayons and coloring each vertex. So, I mean, we could color by members of any set, but usually we just use the numbers 1, 2, 3, K. 1, 2, 3 all the way to K. So some examples. This is the triangle we saw in the previous example as well. Each vertex is connected to each other vertex, so you need exactly 3 colors. This is the generalization with 5 vertices. I put 5 vertices here and connect each pair of them to each other. I will get the complete graph on 5 vertices, and I need exactly 5 colors, because no 2 vertices can be colored the same. This is the case which we call a bipartite graph. A bipartite graph is a graph where the set of vertices can be partitioned. Now here I have the left side and the right side in a way that each of the 2 sides have no edges inside them. So each edge has one end on the left, another end on the right. Or you can do top and bottom or any partition, right? So if you have a bipartite graph, then 2 colors are enough. You can use 1 color for the left side and 1 color for the right side, and that's it, right? So as long as you have 1 edge, the chromatic number will be 2. And this is an interesting example. In this example, you saw I have 3 vertices and I need 3 colors, right? This one does not have a triangle, but it still needs 3 colors. And that's the beginning of the interesting cases. If you try to color this with 2 colors, let's say if I start here, this is color 1, then this is 2, then 1, then 2, then 1, and now here I have a problem, because 1 and 1, they cannot be connected to each other, right? So this will be sort of like the parity condition for Euler. If you have an odd number of vertices along a cycle, you cannot color with 2 colors. But you can color with 3 colors. Just the last vertex, use the 3rd color for it. So color all of them, say red, blue, red, blue, red, blue. The last vertex color green, and then it's done. There are graphs without triangles which actually require any number of colors arbitrarily large. So you say, I want the graph to have chromatic number 1 million, but without any triangles. It is possible. And you can even do it without any short cycles. This is one of the interesting results in graph theory, which is proved using what we call the probabilistic method. We use techniques from probability to prove results for graphs, and it's very interesting. But we don't want to talk about those today. This is a book from, if I remember correctly, 97 or 96. As the title suggests, it's a book dedicated to open problems in graph theory, in graph coloring. And it's like 270, 280 pages, all open problems. Some of them, of course, have been solved since almost 30 years or more than 30 years, 20 years. But some new problems have been added. So actually there was discussions that they are working, the authors, on a 2nd edition, but I haven't seen it come out yet. I hope that it does. This shows you how rich this theory of graph coloring is. And you cannot really be an expert in just all of graph coloring even. You have to pick one area and just advance in that area. And that's what I'm going to do in the next slides. I'm going to pick one area that I picked as a master's student and did my research in that area. So first, if we color, instead of the vertices, now we decide to color the edges of a graph with the same condition. So if 2 edges meet at a vertex, they must get different colors. So it's sort of similar to the Four-Color Theorem again. We were coloring regions, now we want to color line segments or curves. And you can model this as a coloring problem like we saw in the previous slide. You put a vertex for each edge, and then you connect them if they share a vertex. That would be the relation between them. But it's nicer to look at it this way, as an edge coloring problem, as we call it. So you see here I have blue, green, red, 3 different colors at this vertex. Blue, red, green, green, red, blue, and same here, green and blue, blue and green. At each vertex, I have different colors. So again, the smallest number of colors you can do this with is called the edge chromatic number, and we show it by chi prime. Now, there is an interesting result that we need, if the largest vertex degree, like here we see the largest vertex degree is 3. So if I show it by delta, we need at least delta colors. Why? Because at a vertex with degree 3, you need 3 colors, right? You cannot have any 2 edges of the same color. Now remember in the previous slide, I told you the chromatic number can be very large without even having triangles. So based on that, you would expect that here, the number of colors, the edge chromatic number, could be much larger than this delta. But actually, that's not the case. And that's the interesting thing about edge coloring as compared to vertex coloring. So definitely, we may need more than delta colors. So here you see that the maximum degree is 2. All the vertices have degree 2. But we do need 3 colors. As you can see, this edge meets this one and this one. This edge meets this one and this one. So all 3 of them must have different colors. So it's 1 more than delta. This is also another situation which is not so simple. You can see if you start with this one, if I color this one green, and I'm trying to color with 3 colors, okay? So if I color this one green, then these 2 must be different and different than green. So they are red and blue in some order, either blue and red or red and blue. Same goes for here, these 2 edges. Now this edge cannot be red or blue, so it has to be green. Now when you look at this edge, it cannot be red or blue or green, so it doesn't have any choice, right? So we need at least 4 colors. And of course, instead of question mark, if you put a 4th color, orange, you have a 4 color. So we may need more than delta colors, delta being the maximum degree. But actually, we never need delta plus 2. So we can always do it either with delta or delta plus 1. This is called Wissing's theorem. This is one of the fundamental theorems, again, of graph theory. And is dated back to 1964, which is actually quite recent if you think about it. I mean, graph theory going on for 300 years, but this is still like 50-something years old. Now, the four-color theorem is equivalent to this statement. Every bridgeless cubic plane graph is 3-edge colorable. Now, there are a lot of words here that you don't know the definitions yet. I can give you the definitions, no problem. But what is important here is that you see that the four-color theorem, which was about coloring the regions, now is reduced to just coloring edges. So that's interesting. Now, I'm running a little slow, so let me skip the definitions here. Actually, I will not get to one of the problems. Okay, we will see. So this is what we call a total coloring now. A total coloring, remember before we were coloring vertices or edges, now we are coloring all of them together. So here I have 1 at the vertex, 2, 3, and 4 at the edges. So all of them are different, right? Now, the minimum number is called chi double prime now. And we need at least delta plus 1 colors, similarly to before. So at this vertex, I will need 1 color for the vertex itself and delta colors for the edges. So I need at least delta plus 1 colors. But what is, is there an upper bound on the number of colors like in Wissing's theorem was 1 more? Well, we don't know. So this graph, you can see yourself that you need, delta is 3, but you need 5 colors for it. But this is a conjecture which is still open today since the 1960s. The conjecture is by Behzad and Wissing. Behzad was my external examiner for my master's thesis. He is in Iran now, but he was a PhD student in the States, and he was working on graph theory. And as part of his thesis, he made this conjecture. And Wissing, of course, you already heard his name. He was working on edge colorings, and of course, total coloring would be a natural extension of that. So they independently discovered this conjecture, but it's open still. And the bounds that are known are like in the order of delta plus 10 to power 27 or something like this. So any improvement in this area would be very interesting. And as far as I know, there is no recent development here. I want to quickly mention another problem to you, which is also a solved problem. And this is basically the first thing that my supervisor told me when I went to him to ask for, research area for my thesis. But unfortunately, we won't have time to go into too much detail. So a Latin square of order n, like this one is of order 4, is a n by n array of numbers. The numbers themselves are all the numbers from 1 to n. And you want to arrange them in a way that in each row and in each column, you don't have repeated numbers. So sort of like Sudoku, but Sudoku is a generalization of this. So in the first row, you see 1, 2, 3, 4. Second row, 2, 1, 4, 3. Third column, 3, 4, 1, 2. No repeated numbers. Now, finding Latin squares is easy. You just write the first row, 1, 2, 3, 4, and then you keep shifting. And after n shifts, you have, or n minus 1 shifts, you have a Latin square. But there are a lot of problems about them. There are even open problems about them, like counting them. How many Latin squares can you write? Like the one that I have written here is obtained from shifting, but this one is not obtained from shifting. And there is one from shifting. So you are interested in knowing how many non-isomorphic Latin squares can you have, and other problems. What we are interested in here is what we call Dinnitz's problem. Dinnitz is a person who made this problem at 1978. He says, suppose that instead of the numbers from 1 to n, for each cell, I give you a set of n choices. Now, if the n choices are from 1 to n, of course, you can make a Latin square, as we saw in the examples. But actually, this gets more interesting if the choices are not the same. So like, for example, here, I have 1, 2 for this cell, 2, 3 for this cell, and so on. Is it always possible to find sort of like a Latin square here? Of course, if I want a Latin square for 2 by 2, I will need only numbers 1 and 2. You see also 3 here. But this is a more general situation. It's not a Latin square anymore. So at each cell, I have a set of size n. Like here, you see, if I choose 1 and 2 for the first row, then here I need to have a 3 because 1 is already used here. And here I need to have 3 again because 2 is used here. 3 and 3, of course, would not be accepted. Right? So this is not good. And I need to try again. And you can try, like if you use 2 here, then you can use 1 here, and you can use 3 here, and you can use 2 here. Then you have all the conditions satisfied. So this problem actually remained open for like 15, 16 years. And it got solved by a mathematician called Fred Galvin, I think in 92, 93. This is the problem again. You can model it as a graph coloring problem, but now it's a restricted coloring. When I say I want to color the vertices, now here you see for each cell, I put a vertex. This is the 3 by 3 case. Now, since rows cannot have repeated numbers, all the colors must be different. So I put all the possible edges. Here, here, and here. And then for columns, the same thing. And then for each vertex, I have a list of 3 colors which are allowed at that vertex and no other color. And I want to see is it possible to actually color these. Now, I really wanted to mention this to you. So this is the general case where we have a general graph with lists and you can color from the list. This is actually an example from my first paper. I keep mentioning because I want to motivate you that it's easy to get to research in graph theory so quickly, right? I've been talking for only 50 minutes now, and we are already talking about research problems. So that's how easy it is. I don't have time to get into details, but let's just see Galvin from 94, who said, yes, it is possible to do this. And the interesting thing about his proof was that he took 2 results that were already known. Now, these are not necessarily easy, but these are theorems that are already known. So he uses theorem A and theorem B and just puts them together. And that proves the conjecture which was open for 15 years. So it was just a matter of seeing that, okay, you can put these 2 together. And that's it. But of course, it's not always easy to see something. I mean, experts in this area were working on the problem and they failed to solve it. So it takes one observation. And of course, that's the joy of doing mathematics. I mean, you keep pounding at a problem, and when you suddenly see the door open, that's the joyful moment, of course. Let's not talk about this, but I want to talk about this lady here, Maryam Mirzakhani. She was a 2-year junior to me when I was an undergraduate student at Sharif University. She's the first and only female winner of the Fields Medal, which is, your math students is equivalent of Nobel in mathematics, because there is no mathematics Nobel Prize. So she won it in 2014, and unfortunately she passed away in 2017 at the age of 40 years only. Her first paper, I wish I had time to talk about it, but actually her first and second papers were about graph theory. She has more, but as a high school student, she was in contact with some of the professors at my university, and she got introduced to some problems and started solving them. She solved her first unsolved problem, or started working on it when she was only 15 years old. This result that I have quoted here, and it's a significant result, she wrote the paper when she was like 18 years old. So again, an example of how easy is it to get into research in graph theory. You just need a couple of definitions, and then you can start working on the problems. So hopefully we can all aspire to her. I wish I had 1% of her achievements. But yeah, I'll stop here, and thank you for your attention. Questions? Yes?
Is there a relation between graph theory and geometry? Because we see some of the graphs and shapes.
Yes. There are, different areas of mathematics. Any place where you see objects with relations between them, that would be considered a graph, right? But when you say relation, mathematical relation. So, are there cases where a theorem in graph theory has been used to prove something in geometry, or a theorem in geometry has been used to prove something in graph theory? And the answer in both cases are yes. And you can see like the four-color problem could be considered a problem in geometry or a problem in topology. But in nature, really, it is just a problem in graph theory, right? So there are many examples, yes. But I don't want to get into details. Any other questions? Okay. So actually, one of the problems that I was sort of thinking about putting on the presentation and I didn't is a geometric problem, which was discovered, asked by an undergraduate student in 1950 something. And he was only 18 years old when he asked the problem, 18, 19 years old. So let me mention that problem to you, since no one else has any questions and you asked about geometry. So again, it's a coloring problem. Imagine in the plane, you want to allocate a color to each point. Now here we have infinitely many points, right, in R2. So each point gets a color. Now, the key here is that if the points are at distance 1, you want them to have different colors, right? So let's say if this is distance 1 here, then these two must get different colors. Now, what is the minimum number of colors? Actually, is it possible with a finite number of colors? And what is known is that you need at least 4 colors. Let me show you why. Because I can draw an equilateral triangle. Now, of course, the triangle we saw in the slides, we need 3 colors, right? Now, I can flip this over. Now, if I have only 3 colors, this one must be 1, because it cannot be 2 or 3, right? Now, I can take this configuration and rotate it. So let's say I rotate it up to here. I rotate it until the distance here is 1, right? So now, again, if I have 2 colors, 3 colors, this must be 1, but now I have a contradiction because I have 2 points at distance 1, both of them with color 1. So you need at least 4 colors. And it is proved that you can do it with 7 colors. So the number of colors, if I show by chi, this is between 4 and 7, the minimum number of colors. But this is open for 65 years now. No one can make any, adjustment. Even go to 6 or show that at least 5 colors are needed. It's not been done. But this is a very easy problem. And like the other problems, like the 4-color problem, which is Four-Color Theorem now, people have been working on this. And they have been making side results, which are interesting. I have one paper in this area, even though I did not touch any of the 2 bounds, 4 and 7. So you can start working on any problem, like this problem. You may not solve the whole problem, but you may be able to make a small, advancement in some direction, and that would be a research paper. And it could be very significant. I mean, something that looks easy to you, it could be significant for others, like the example of Galvin that I mentioned earlier. He just made an observation that you can put these 2 theorems together to solve that problem. And it's not necessarily difficult when you, put yourself in his shoes. He didn't really do much work, but he proved something very significant. Okay, thank you for your attention. And